Perfect. Hi, everyone. Thanks for coming to this talk. Today, we're going to continue on the graph theory and stuff presented by the previous talk, essentially talking about relation-based access control. So what is it, and how do we make it happen? Right, so I'm Lucas. I've been in the Kubernetes space contributing since 8 years back or something like that. Been doing some installers, some security things, but also quite a lot in the community, like driving the meetups in Finland around this space and so on. Now today I'm working at Upbound, a company doing control planes. And well, I'm also studying at Aalto. So for the people that are building the secure systems, or trying to at least, users often have this kind of mentality on their side. We need to build a secure system, but we still need to be able to do anything, right? And it follows this recurring pattern of, I wish these parts, this is the classic XKCD, I wish these things could communicate more easily. Then we make them communicate, security bugs everywhere, we need to close them down again, and so on it goes. You can see this with VMs, containers, WASM, all of these things in the cloud and so on. So the landscape is changing because, well, also as in the previous talk, more things are moving to the cloud, more things are becoming API-driven, and we're quite good at the kind of perimeter security thinking and networks and stuff like that, but we don't really have a good idea of what is happening in the APIs and how to defend against those when there are multitudes of APIs. So tens, 50, 100 of APIs in an organization, usually something like a software as a service. How do we map credentials of different things there and what they can do and kind of traverse that graph? So this leads to fragmentation eventually, where we have a lot of different services with completely incompatible access control mechanisms, not like the kind of Active Directory unified thing. So what do we do? Then if you're writing an API, then this is quite familiar as well. This is now in the last OWASP, it rose to the first and foremost broken access control in the object level, and then the third one being the property level. Here in the object level one, we're talking mostly about kind of the first authorization layer, where we determine that should this user, without even looking at the payload sent to the server, should this user be able to at all access this object. But then on the property level, we are getting a little bit more contextual and kind of looking more at the attribute. Should this person actually be able to modify this specific attribute, this specific property in the field? And these two are kind of conceptually different. So for the first one, this one we're going to talk about relation-based access control. For the second one, more around policy engines, and then we'll see how they complement each other in a kind of uniform API server setup. So let's first dive into 4 of the challenges with building a system that needs access control, so every system. The first one being like uniform enforcement. We need to, these are both kind of solutions and challenges at the same time, but if we have the policy enforcement and the policy decision kind of computation in the same place, it's getting highly conflated. So if you have an API server with, I don't know, 100 eventually if checks, you look at the JWT token and then you just like, if group is this, right? If group is admin, then they can do it. Okay, sure. If group is employees, then they can do that. But then if it's employees but not this, then they should do something else. And eventually, because it's Turing complete code, you have no idea what it's going on. And because you have it in the same package with all of your other things, chances are that you're not testing it so well either. But if you separate them, then you can actually start doing a much clearer kind of intent-driven testing on this. Even if it's in the same code, just behind an interface, where you then instead, oh yeah, it's true, now these come again, where you instead have something that is actually built for managing policy, right? So a language which is has some gives you guarantees on, for example, that if you deny, then it will always be denied, or that it's denied by default, or that it's actually chaining the things correctly. Open Policy Agent from Stura and CEDAR from AWS are two good such ones that can kind of help you with this, with a purposeful declarative language instead of this that you can actually check instead of this, ad hoc if statements in your code. Right. So then, and if you go even further and actually make this interface, then you will end up at something where you actually you resolve the principle, so the user or subject of that is trying to do something, the action, the resource, you normalize these, and then you collect unified attributes. And then you can reuse and reuse these across your system. So with this, then you need to ensure correctness. And here, that is a challenge, but you can use things like unit test, of course, but then if you have a language like CEDAR or OPA, then you can actually do more static analysis. You can start fuzzing the things, see that is the thing that's coming out of my policy is actually the thing I want. And Amazon, for the CEDAR language, they use something really cool called differential testing. Then policy equality, most of the bugs actually arise on upgrades. So when you refactor, when you're thinking, I code something now, and then in a half a year I'm thinking like, well, why did I add that, part of the thing? This shouldn't be never used, right? I remove it, and I didn't have a test for that one line because I didn't think it was important, of course. So then, something crashes then in production, right? Because it was an edge case. But if you have a language that is declarative for specifying that policy, then you can actually have a canonical representation of it, which you can check for equality. And then a good way to roll out to ensure yourself of the correctness of your policy is to do a shadow rollout. So you roll out the new policy, but only while still enforcing the old policy, and just checking that does the new policy return the same thing as the old one. And you, of course, audit log that and kind of warn if or big errors, in your backend when it doesn't. Then a really tricky one is preventing privilege escalation, because often users expect these kind of drive things and GitHub and all. You can manage in an organization there a lot of things. You manage other people's access. Often through these properties, that was always number 3. How do we make sure that these don't actually end up somehow in the kind of network, the graph of access control? They end up escalating. You give someone else access that you didn't yourself have. Then the cap theorem. Okay, that is a fun one. So we have kind of 2 traditional approaches, right? The kind of offline only, where we have a credential, a GWT token, cert, client cert, or something like that, and then we just look at the thing. Is it the group admin? Sure. Okay, then I'll allow it. If not, then not. But it can't really be revoked. So it's very hard to revoke it. So is that a good trade-off? I don't know. Then eventually, on the other kind of part of the spectrum, you have these kind of where you only have the credential ID in the credential. Everything else is in some database. But then you actually need to check it every time, which creates kind of a single point of failure for this authorization system that you're making. So then you have to start thinking in pure cap fashion that, do you sacrifice the consistency or do you sacrifice availability? Is it okay to cache? How long is it okay to cache if your authorization system goes down, if you have a separate one, so on and so forth. Then some other things, well, in large organizations, in complex systems, the JWT token is not really an option even if you have a fine-grained architecture, because how much size do you even have it in the token? Like if you have, I don't know, 1,000 projects in an organization and the user has access to 500 of them, do you put the ID of 500 projects in that token and pass around 2 gigs of data every time you log in? Probably not. And if you have these kind of policy engines, if you need to take in a lot of data for making that policy decision, do you even have enough, in larger organizations, do you even have enough working memory, enough RAM to put that and process that in just one place? Because the dimensionality can be quite high, which exponentially really explodes the size of what you need to, the data you need to process. Then that's why eventually you will need a database if you grow big enough. Then in the kind of consistency versus availability again, how long can you wait before a change needs to be applied? So similar, how long can you wait before you need to revoke something? How long can you wait before a new permission actually needs to be seen in the system? Is it a millisecond or a year? It really depends on the organization. Then Google, in their paper about Zanzibar, which we'll come to later, just in a bit, talks about casual ordering. So they call it the new enemy problem when essentially you get the applications of policy out of order. That was meant. So when we fail to respect the ordering between ACL updates, or when we apply old access control kind of capabilities to the new content. So a classical example is if you add an allow and a deny at the same time and then they get out of order, then you have problems, essentially. Then time complexity, once your data starts to grow, once you go fine-grained, how does your latency scale as a function of your graph? So if you're just, is it linear, is it cubic, quadratic? Nobody knows until you actually, run into it, and then you need to refactor your system, right? Most likely, if you're naive, then it will be quite high an exponent if you're not thinking hard about the problem. Then fourth challenge is observability. So can you explain why you got the decision you got, right? Can the machine give you, when giving an access, you have a check request, then can you actually know at the same time why was this check allowed? Ideal if it's both in a way that a human and a computer can understand. That's quite rare, I feel. And then can you look up all the things that you can access? So can you, for example, Google Drive and these kind of systems you can, just because Google Drive is built on the system that I will present next, right? But that is not, again, it's a hard problem once you start thinking about it, because in a kind of ABAC fashion, when you just say that everyone with the attribute admin can show this thing, right? Or everyone with a JWT token with employees can show this page, then you still don't know who is everyone with this thing, and kind of a combination with those. Like, of course, if it's just one property, it's easy, then you can do a select of your employees table and just be done with it. But once it kind of starts getting into this Turing complete code that you don't understand, when it's more than 10 lines, we really get lost. You're lost in the trenches. And then the reverse lookup as well is interesting, that like, okay, I have a file or a resource, and this, the hacker got to this resource. How did they get here? I have no idea. Then the graph, I like the Bloodhound graph from the previous talk as well, where essentially you see this immensely big graph, and there's paths everywhere, and you don't know, you can't comprehend it. Humans, it's just beyond our cognitive capacity. So then finally, of course, audit log. Do you actually get it in some structured format that your audit log can use, that you can actually processed in some semantic way, or is it just arbitrary characters coming after each other that you need to process and interpret once again in some kind of Elasticsearch? So yeah, this kind of leads us up to the into the relation-based access control. So what kind of, these are all challenges, it's hard. What can we do about it, and what have people learned when building large-scale systems that already exist? So even though we don't have a large-scale system, we can benefit a lot from them. So next generation access control, NGAC, is a standard. I think it started in 2013, then updated in 2018, and then I saw a revision in 2020 as well. It's developed by NIST, so the Standards Institute, one of the standards institutes in the US. It proposes a graph-based mechanism for essentially that can emulate all of RBAC, ABAC, multi-level security, so like military-grade things where you have classification labels, separation of concerns, and that kind of stuff. Then, so that's one standard. It's a standard. I recommend reading it. Then Google wrote about in their paper about Zanzibar, how they actually have one big graph for all of the Google products. So you as a user, you have one UID in this graph, you're one node, and then everything you can access in any Google service is just in that one graph, which is really amazing to me that they managed to do it. And it's, as we'll see, it's amazing how few, both in NGAC and in Zanzibar, how few primitives, kind of core primitives in the graph you need to actually build a system that both scales and works for real use cases for all the things that we use every day, right? So the core idea is to compile down the access control problem of like, should I allow this access or not, to just, is there a path in the graph from the user node to the resource node through a specific typed relation? So get, post, whatever you want, view, something like that. So this is the kind of core idea of this talk. So a little bit about the developer experience. Say that you're a developer and now you wanted to use relation-based access control. What do you do? Well, you first need to define the type or the schema of the graph. So for example, you have a folder system. Users can read or write folders, and folders contain documents. Okay, so we have three kind of relations here. This should be double, right? So read and write, and then contains. Those are the relations that exist between these three types. Okay, and then when we have this model, we know all of the things that are kind of allowed in this graph. So then we can start adding data. We can start add kind of concrete edges to this graph. By default, there are no edges at all, so no access to anyone. But then we start adding this edge. User Lucas can read folder customers. Then we add this edge. Folder customers contains document secret, and folder customers contains document foo-inc. Sure, now it kind of starts to look, it's simple, but it's something. What can we ask what can we know then from this graph? We can ask that, can user Lucas read document secret? Yes, there is a path there, specifically involving read, but can I write document secret? No, I can't, because there is no such relation here. But then I can do the lookup and ask which documents can I read, and then we see that I can read these two. So that's a simple example. Then let's look at who is using this, right? So, well, it's the Zanzibar methodology came out of Google, so of course Google is using it for all the things. Then Airbnb has built their system around it, just their own implementation based on the paper, essentially. And then Carta as well, Airbnb, probably most people know, but then Carta is a kind of equity thing where they have a lot of kind of stakeholders. So they also needed this because their kind of ad hoc authorization solution wasn't scalable enough in their organization. And essentially every time they needed, both in Airbnb and Carta cases, there's good in the Authorization at Scale podcast, you can find it on Spotify or whatever, they talked about this, and they both kind of saw that every time they made any single change, once they were kind of big enough, it just like slowed them down, added more inertia and more inertia all the time, because the system didn't scale from a kind of organizational perspective. But then there are open source versions of Zanzibar. The two I will have looked the most into and kind of recommend here is SpiceDB, and then also a CNCF project called OpenFGA. Stands for Fine-Grained Authorization. And then here are some kind of companies that are using that. Volt is using OpenFGA, Stacklock as well, and Canonical, and then Netflix and GitHub have been doing some collaboration with SpiceDB to kind of add features and make them production ready. So I don't know if they have not announced that they're using it, but at least they have invested time to make features into it, so that's pretty cool. And then NGAC is a standard. It has no open source implementation as far as I know, but I spoke to some Tetrate guys, and they are kind of, they have their version of implementation of that as well, which is quite cool. So let's look at a little bit more complicated example than the first one. That will be a bit more concrete about what the types actually are in the graph. So we have a user and we have teams. And there's a relation between team and user called member. Clear enough. Then we have a role, and we can have assignees of the role. Who can be assignees? Well, users can be directly assignees, but also members of teams. So in both cases, a type. So why I have this is the color for user. So why I have this relation here in the same color is because the assignees of roles are all users. So if you would do a reverse lookup, you will end up at user nodes always if you dereference it fully. It's not teams ever, because we're always assigning team members, which can only be users, right? Then we have a folder, and we have now kind of 3 levels of access. Now, I made these up. We could have something get, post, put, patch, whatever, as well. Or anything arbitrary, but now admin editor viewers is clear enough to understand. And now I can say that role assignees of a specific role can be, for example, have admin permission to some specific folder. But then I will also say that I don't want to kind of make 2 edges in the graph, or 3. If I wanted to assign someone admin, I want them to also have editor and viewer kind of implicitly. I don't want to have to create 3 specific edges to this. It should be enough with 1 and then have them inherit. So an admin is also an editor is also a viewer. That is these things here. And that's in the schema. That kind of always follows from the schema, and that's part of the evaluation of this graph. Then folders, the green one here. So these blue ones are for the kind of what's evaluated. The white edges here are the things that you actually define to the system. And then you also define the green ones, but the green ones doesn't include any user. It's kind of meta relations between the resources themselves, not between users and resources. So folders can have a parent relation to another folder, so you can have subfolders, right? So it becomes a tree like that. And then you also have documents. So now you have the same thing, now just put them for clarity, admin, editor, viewer, upwards like that, which you'll see why I did that in a second. And then, of course, there is a kind of resource-to-resource green relation between these ones, which is that a folder can contain documents, clear enough. And now the interesting thing is that we can say that, well, if you're a viewer on the folder, then surely you can view the document. If you're an editor on the folder, then you can view the document, etc. And you already notice here that there's multiple paths between, for example, if I'm a user and I'm checking for viewer, do I have this relation? Then I can actually traverse through this path and go that one, or I can go here, editor, hop to editor here on viewer. There's multiple paths in this graph that kind of makes it work. But then I can also assign kind of role assignees to directly to specific documents. This you can do in Google Docs, for example. You can share it with an individual user, with a group, with all kinds of entities. So now this is a schema. This is kind of what you define first. And this then kind of tells what relations are even, what nodes and edges in the graph are even kind of possible. For anything else, you will get an error. So now that I have that, I'm going to add some concrete data to this. So I'm going to add user Alice, user Bob, and they are a member of team employees. Then I will make Alice an admin, or well, assignee of the role admins, and anyone that has is in this role, then they get admin on the whole Acme Co folder. Okay. Then the Acme Co folder contains a document called salary info. Okay, so this should not, everyone shouldn't necessarily see this, but fair enough. Okay, and then we also the Acme Co folder for the whole company also has a dedicated subfolder called public. Fair enough, it should probably be shared with everyone, right? We have the inheritance there, and then the public also has a document called templates for, I don't know, some text. So now, lastly, we say that everyone in the company, everyone in the team employees, they can edit the public folder. And note that these are directed edges, they don't go the other way. So even though you have editor and folder public, you can't do anything to folder Acme Co naturally. You can do bidirectional, but then you actually need to assign both ways. You need to be explicit about that. So now we have the graph, great, what can we do with it? Now we first ask what documents does Bob have access to? Okay, so I'm gonna go with red here. So Bob is a member of team employees, assignee of public edit, we get an editor there. Within this we also have the viewer, and now we actually can traverse down to documents. So now we see that Bob is both a viewer and editor of document templates, but nothing else. Okay, but that's what we have now. We know that Bob could do this well. Then we go for Alice. Alice is a member also of the same team employees, but also an assignee of the role admins, right? So now we kind of traverse kind of this graph in parallel. Then we see that, okay, we have a direct assignment to the admin here and editor here. Then we traverse it down within the same type. This is not how the actual algorithm works, but conceptually. And then we see that actually here, so notice that we didn't have admin on this one before, but we should, because admin should traverse from the parent folder. So now we add admin there on the subfolder as well. And then we go to documents, so Alice can do anything on any document, right, in this tree. Okay, so that's a relation-based access control, and this scales incredibly well. Of course, not for everything, but for a lot of things, which can be seen by the users of this. Another thing, when we said that it can emulate a lot of kind of different paradigms, this was role-based access control. So we have now shown that we can do role-based access control in the graph of RBAC, relation-based access control. But can we do ABAC? Can we do attributes also with this graph? Well, let's see. So we have now 3 workloads. 2 production workloads, 1 in EU, one in US. Then we have a development workload in the EU. Okay, then we kind of create these attribute region, EU and US, and then environment, prod, and dev. And we say that, well, we connect these to each other, so that we say that region EU, well, that surely they have a connection with this workload and this workload because they are in the EU. This one is in the US, so it should have a relation to the US one. Then we define another dimension of this. We define now environment. So we have now the environment prod, that's these 2. Right, and the development is here, right? So, and then I'm gonna just arbitrarily give myself permissions on these. So let's see, I wanna be able to read and write anything in the US, in the EU, because that's where I am. I shouldn't be able to touch anything in the US, right? Because I have no edges there. Other people should, but not me. But then I should be able to read anything in prod, but I should not be able to write anything in prod. I don't trust myself for that. And then, I should be able to do anything in dev because I love hacking, right? So let's see what of these things should I be able to access? Let's see. It starts looking like this. And notice that here is an and for all of these, because now we want to show that, well, we could have an or as well. The previous example was all unions, so all or. Either I have this, or I have this, or I have this relation. But now we actually force that for me to be able to read the resource, I both need to have a kind of authorization to be able to read in that region and in that environment, right? So that's why I need both the edges here. So, and that's the kind of interesting thing with Zanzibar, is that we have essentially covered all of the data elements already. Like that, there's nothing more. There's the kind of, you can assign direct user to something. You can assign sets of users to something else. Those are the two only assignments you can do. And the three rest of the data types comes from the schema. You can either kind of traverse from admin. You can say that any admin is also an editor. Or then you can say that between types, the same thing, so that parent folder should, for example, see documents or kind of traverse documents. And the last thing is just set operations, so or, and not. That's it. There's no other data types in this graph, which makes it extremely performant, that we'll see in next. But I think it's really incredible that Google, for all of their products, managed to put all of the things in the same graph, and it just boiled down to these 5 operations. So essentially, like we have a computer, there are only so many. Well, I know that x86 and some other instruction sets are quite bloated these days, but logically, we could implement a computer with just the move command. So it's kind of interesting to see the same thing, that we essentially, this is just additions, subtractions and stuff, but we still make up a fully working system from this. So what should I be able to access? Let's look up. So I should be able to read the fraud backend in the EU because I have both of those permissions. But I shouldn't be able to write in the production in EU because I shouldn't be able to write to any production. I should not be able to touch the US one at all because I don't have any permission to that. But then the dev backend in the EU, I should be able to both read and write because I have all of those permissions. So it turned out that, okay, I could do I have some relation to this, not all, but all of these relations and none of these. So this is kind of implementing the attribute-based access control. So now this kind of begs the question, is this the lingua franca of authorization or access control generally? How much of all the things that exist in our system can we actually map down to a graph which we can inspect this clearly? Can we, if we are thinking that we're living in an API-driven world where we have hundreds of different SaaS services, and all of those have different permission systems. We have our own key cloak somewhere, we have AD somewhere, we have production environment somewhere. Can we actually just for understanding it, can we just extract the data? The authorization is enforced where it's enforced, but can we kind of just take the data, just read the data, put it into the same graph, and then see that what can our employees actually do? And then by having a performance graph engine actually see, oh, I didn't expect my developers to be able to traverse this system, and then this system, and then this system, only to get to my production. Oh, that was unexpected. And there, so far, but before these ones at least, not that I know of any, standards for comparing, merging, joining different types of authorization systems. So RBAC can maybe do this. So because we can emulate these other kind of higher level, and for sure users should still think about, I'm not saying that people should start thinking, when you are a user, you shouldn't be thinking, oh, I'm adding a graph here, edge here. You should still be thinking in these kind of terms of higher level things like roles and attributes and stuff. Just as most people write their programs in Python these days. But this is the kind of the bit level things of of the system. So I think about this graph as kind of a highly optimized index for our access control. So if you compile down your existing data, although it's enforced in other places, into the graph, then you get these lookups extremely fast. We'll look at the performance soon. We get a consistent data format. And then we can actually audit the schema, or like the data, what can people actually do here? Because I can't visualize it, no one can. So extremely fast, I said. Well, I'll let you judge for yourself. So from this SpiceDB load test, they spun up a lot of nodes in AWS. They made a graph that was kind of social media-like. You know, you have, so it has a fair amount of nesting. You have posts, and you have users, and you have different kind of topics and stuff. And then they added 100 billion edges into this graph. So more than most kind of normal organizations still. And they added this to a kind of Pareto distribution, so that actually follows most of the actual social media graph. They put 1 million requests per second towards a cluster, check requests, to read. And then they put, to make it not kind of, because there's caching, they wanted to make it kind of real world. So they actually put 1% also writes all the time. So there were no kind of place where the authorization actually was static. And this 1% is more than Google actually wrote in their paper. I think there was maybe more like 0.0% or something like that. 0.7, sorry. And there we got 3 milliseconds for the mean of the request. It traverses quite a lot, but it does some really amazing caching. And even in the kind of worst case, P95, we got 6 milliseconds. For still, like, it's then still kind of looking at this graph of 100 billion edges. So it's not kind of, even though you put this in the critical path, it's not that bad, really. Like most likely you have something else that's way worse performing. And the writes weren't that bad either, comparing that now it needed to do this kind of recaching and stuff, but then still 16 milliseconds the mean, and P95 around 50. And this is before they even have made the Leopard indexing system, which makes which actually resolves the deeply nested things and provides a cache index for that. That's the next feature that they're coming up with now as well, which will even increase kind of the performance of these. So we talked in the beginning about policy engines, and now we have talked about RBAC data stores. What is the difference? I want to make this clear that there are different things. They should be conceptually used for different purposes, right? So one, the RBAC data store is stateful. You will really want you to put the data in there, even if it's just an indexing, not even for enforcement. But then the policy agent, like Open Policy Agent and CEDAR and these kind of stuff, they are mostly stateless. It's mostly, you have some kind of logic, authorization logic of like people should not be able to run containers with this, malicious domain or something like that. So that's mostly stateless. Maybe you update the domain names, once a year or something like that. Or maybe you load in one JSON to verify something, but not really any like big data. But then the RBAC gives you allow or deny, but the policy engine can give you, for example, a rate limit, a number back, or a list of things or something. So you can get anything there. Then the typing in the RBAC data store is strong because it actually needs to know all of the possible paths in the graph to compute it quickly. But then in the policy agent, you can accept almost any arbitrary data and just check that if this field exists, then I'm going to check it. If it's not, then not. Topology in the RBAC, you have a centralized server, but then in the policy engine, you can be anywhere, essentially. Like it can be built into programs, it can be on the edge, it can be kind of anywhere. Technically, you can do it with RBAC as well, but it doesn't make as much sense. Policy updates you do via the API to RBAC because it's a long-running process, but the policy agent mostly runs out of band in places so that you actually need somehow to update in your own way, which kind of introduces a policy risk of these privilege escalation things, right? But in the RBAC, the benefit of it, you can actually look up all of the resources, because that's the whole point, you put them there. But with a policy engine, you can just say that everyone, with some property or some attribute would be able to do this, but I don't know who has that attribute. Consistency in the RBAC data store is strong. Even the SpiceDB even mitigates a new enemy problem, so you will always get a casual ordering between your writes. So it actually kind of is fully consistent, of course, if you have a consistent database. But the policy engine is eventually consistent, because if it's something somewhere executing some JSON script or some other type of policy file, then you get the file there when you get it, right? No guarantees. So RBAC is best for these kind of hierarchical roles, attributes, these kind of things that we have shown here. But the policy agent is really good for some kind of more complex ABAC flows, where you actually need to inspect some payloads, for example. And then in order to do the attribute ABAC thing that I showed, you actually needed to do some pre-processing of the object, like the index thing I said. You need to actually know what the object was, put in the attribute nodes in that, and connect them. Only then you kind of got the thing, but policy agent doesn't care, it just has whatever. So putting it all together, if you want to make a secure system, what do you do? Okay, so you make an API server. This is what most people have. Well, you first need to authenticate. First you do a max in-flight requests limit, so you don't get DOSed. Then you authenticate, look who is here. Then you check flow control that, well, this maybe the same user shouldn't be eating all my CPU. I'm going to put a cube behind this one so it doesn't, so I kind of prioritize other people as well, system users. Then I start authorizing, okay? I authorize, I send a check request to the RBAC database, RBAC server. It has a database, consistent database in the backend. You get a response, okay, it's allowed, perfect. If you have then if you send some payload, then you run this payload through admission control, and well, you ask that, is this payload okay? Should I be able to store this to my database? And then it's a perfect way. So you see, I have both in this picture here. I have both the RBAC server, and then later the policy engine kicks in and looks at, is this now a good manifest? And then when we know that it is, then our authorization state might have changed. If we issued an update, then we actually might need to update the graph as well, the relational database, at the same time. But so then we write to the graph, but then we also actually need to compute that we don't kind of escalate the privileges of this user, and that they actually only add such connections kind of from start to end that it already has access to. So we try to not escalate the privileges and then write to the database. Then first we write to the storage, whatever database that is. And when we get a response from the storage, we might get a list if we're listing. So then actually we might not want to let this user see every other user in the system. Maybe the manager should only see the local team, their data of the local team. So then we actually apply a list filter. This we also can ask from the RBAC database. Because the policies might be coming from so many different places that it doesn't make sense to put this into the API server with a lot of if checks again or for loops. We just do a list resources here. And first then, we go back to the user. I'm sorry, it was quite hard to make a picture that would make sense for this kind of thing. But this, I hope with the animations, it kind of makes sense. So these are the steps of kind of what what a kind of decent API server should do, right? Does most of the API servers do this? I'm not sure. Probably not everyone needs it, but at least this is a kind of good baseline. Of course, we have the audit log doing whatever is on the request. So if we have a framework of API servers that look like this, we scale these API servers up, we kind of add our types to it, then we might be in a quite good place for our own stuff. But then, finally, we want to still have those systems we can't control, whose data we want with a reconcile loop, a controller, to read that data and write that data into the same RBAC server, so that we can actually understand what can they do in aggregate. And yeah, that's essentially it. So I said in the beginning, I'm a kind of been a Kubernetes contributor for a long time, soon 10 years. So of course, I need to give a mention of that, because Kubernetes actually implements this in its API server. It has all of these steps, and it's pluggable in each step. So we can actually, by just extending the API server, we can get all of these things kind of today. So Kubernetes is not, I don't think of it as a container system. I think of it as an API runtime, a kind of control theory kind of framework that on top of which we can build platforms. They don't need to be cloud, they don't need to be containers, don't care about that. There's two distinct layers in the API, or in the code base of Kubernetes. There's this kind of control theory thing, which is just kind of borrows a lot from the real world. On like, we need to always check, you need to always kind of be declarative, say where you're going, all of these things. But then on top of that, it just happens to be built a container orchestrator. But we could write so many other things, and people do. So it has it already. It's fully extensible. So then OPA, Open Policy Agents, CDAR, Common Expression Language, they are all kind of good implementations of policy engines with these properties that we talked about. SpicyDB, OpenFGA are good open source implementations of relation-based access control. And so, which means that you don't have to make it all yourself. There's some really kind of hard problems with the graph traversing for sure, but these already have done most of it. So instead of doing it all from scratch in every API server you write in TypeScript, don't kind of build all of these things yourself. Use the stuff that already exists. And then you can join us on this journey. Join me on this journey of kind of actually exploring this kind of generic control plane, making stuff that makes sense for generic API servers, such that we can build higher level platforms on top. So that's the talk. Thank you.